Okay, so here's my official welcome to the class. So welcome to fall semester. This is going to be an interesting one, I think. A lot of potential, a lot of challenges ahead of all of us, and welcome to CprE 381. Hopefully, many of you had a chance to just introduce yourself to some randomly selected classmates. We're going to try to do that again at a couple points later this semester. I should introduce myself. So those of you who don't know me, my name is Joe Zambrino. I'm a professor in the department. I've been here for 14 years now, and this is one of my favorite classes to teach. So my academic training was in computer architecture, and I do a lot of advanced hardware digital design. And so the interests of my research and interests of this class intersect quite nicely. And it's a class I've gotten a chance to teach a number of times, and I'm looking forward to it this semester. It is a weird environment. This is not how I would prefer to start the semester. I wish we were in a nice big classroom. But we're gonna make the best of this situation, and I think we can. I think the labs will work well. I think we're gonna be able to support you as best we can in this virtual environment, and we're gonna have fun with the technology along the way. I do have everybody else in the class muted, and I think that's probably for the best, just by default muted. We could experiment with you just unmuting yourself and speaking up when you have a question. You can also try, whether I'll be able to see it or not, there's the raise hand feature in Zoom. You can also try typing something into the chat. If there was a pressing question that happens in class and I just missed it, it's not the end of the world. I'll get to it offline and post a separate video or do something there. I prefer a much more discussion-oriented classroom. I prefer much more back and forth, and we oftentimes get to go on really fun tangents in a class like this. It's just going to be hard to manage using Zoom, and I'll do my best, but feel free to raise your hand, feel free to ask questions. I may not get to them as quickly as if we were in the classroom and you could just speak up, but we'll do the best we can with we have the technology available to us today. Let's get started with just the beginning. I think it's probably more important than in most semesters to get to sort of the syllabus type topics today. But even again, if we don't get to all of those, I will make sure that I provide an update video with all that additional information. Let's give it a try here. So on Canvas, you can find these slides, and we'll walk through Canvas together briefly here. But this is sort of our main introduction topic here, where we get a general feel for the course, what we mean by computer organization as a topic for a required course in the computer engineering curriculum. Let's start with a very little bit of computing history. I'm curious if anybody knows what this computing device is. Well, don't all speak up at once because I don't actually want you to. This is the at-Nassau Berry computer. This is Iowa State's main point of pride from 1942. So this was known as the first electronic computer. There's all electronic computer. There's other computers that have certainly an earlier claim to fame in terms of being a computer using electronics. There were other computers that came at around the same time frame that were much more programmable, this computer. But this one gets some claim to fame as being really sort of the first electronic computer developed right here on campus in electrical engineering. And this is John Vincent at-Nassau and Cliff Berry. At-Nassau was teaching physics at the time. Berry was a graduate student in our department in electrical engineering. It didn't get as much fame when it was first created because of World War II, and it was abandoned for a period of time. And there's quite an exciting history about this device, how it was developed. There was a replica of this sitting in Durham Center, but it's not there currently. It's on loan to the Computing History Museum. There's some remnants of it. One of the original memory drums is available, and you can go check that out the next time you're on campus and happen to be in Durham Hall. So that's 1942. That is a very long time ago, right? That's approaching 80 years ago. It is sometimes interesting to see what are people's projections, in the future. What will computing be like in the future? And here's just a very simple sample of computing of the future. So I don't know how well you can read the caption here, but what it says is scientists from the RAND Corporation have created this model to illustrate how a home computer could look like in the year 2004. To the extent the technology will become economically feasible for the average home. And this is actually a work of satire. But if we look at this projection for what computing could look like roughly in this generation today, Well, we see some things there in that picture that make some sense, right? So there's certainly um, there's certainly the keyboard. That's some sort of keyboard device. It's connected to a printer, but that's fine. We oftentimes have that. That's a television screen, but you could think of that as your monitor. There's a whole bunch of gauges and switches and things like that. But some folks who build their flight simulator rigs have something somewhat similar to that. And then of course now we have the boat style steering wheel. And I don't know exactly what that's for, the steering wheel. I just know that I kind of want one for myself. I don't have one currently, and I'd like to have one on my next computer. So we know that's not what actually the evolution of computers wound up being, in going from the Atanasoff-Berry computer in 1942 to computing roughly today, right? We know, certainly those in computer engineering and associated disciplines, that computing is everywhere. But I think even as computer engineers, it's sometimes possible even for us to kind of underestimate the ubiquity of computing. We know some of the, I guess, common examples um, of, let's, one second here. We know some of the common examples of computers that are in our smartphone, and we know that that's a computer that does all the things that we consider a computer being. And we know, of course, there's computers in our automobiles, but we may not, even as computer engineers, appreciate the scale of the computing that's happening inside a modern automobile. Of course, computing inside our video game systems, they are essentially just computers with a somewhat dedicated task associated with them. Computing in our networking equipment, as well as our supercomputers, and computing inside all of our robots as well. But even as computer engineers, I think it's often the case that we don't appreciate the entirety of the scale of what size, scope, quantity of computing all around us. This is a class on computer organization, and something that we need to keep in mind throughout is that when we refer to a computer, there's, no matter how large, how small, from our supercomputer to our smallest embedded device, any computer has the following five parts associated with it. And you can divide any computer, no matter how primitive or advanced, into those five parts. We think of first of sort of the input, right? We need to be able to do some interesting computing. We need to be able to bring data from the outside world in. And that's represented here as an input or an input device. You can think of that as the keyboard you're typing on or the mouse, but we also think of our storage, our disk, or our network as being an input device. That's getting things into the computer, getting data from the outside world into the computer. Generally, and almost all computing has some concept of this, there's this place where that data is stored when it's time, until it's time to do some processing on it. That's the memory. That is the storage of that data inside the computer. And then the actual processing is happening there in the so-called processor as part of the computer, where we can also separately subdivide that into the actual computing hardware that's doing the arithmetic. That's referred to as the data path, and we'll use that term a lot. And then the actual control logic inside that processor, the so-called brain, the decision making. If the computer was only doing arithmetic, we wouldn't really think of it as a computer. It'd really just be more of a calculator. But when you add that arithmetic to the opportunity to make decisions based on the results of that arithmetic for data that was brought in from the outside world and stored in memory, then we have so-called control, and we have something referred to as a processor then. Control and the data path does the computation, stores the result back onto in memory, and generally the assumption is ultimately there's some output device that we care about. So input is bringing data in from the real world. You can think of that as your keyboard. That's fine. That's the easiest way to think about it. And then our output also has to go somewhere, whether it's stored on disk, displayed on a display device, or just off over the network. So we talked about some of the very few big picture takeaways from the first day of this CprE 381 class, and that's one of them. That any computer, no matter if it's a supercomputer or the tiniest embedded device, has those main five components to them. And when we think of a class that's referred to as a computer architecture class or a computer organization class, and we'll use the terms roughly equivalently this semester. In its broadest definition, computer organization or computer architecture is the design of the abstraction layers that allows us to go from an application, something that we want to accomplish, to the underlying messy device physics between it. So there's a lot of layers that we design between those, that very top level application. Here is what we want some computer to do, whether it's to manage the autonomous driving in our vehicle, or just receive a cell phone call. And then there's the underlying physics, whether it's wireless technologies, whether it's the actual semiconductor physics lying underneath it. So all of computing is the design of those abstraction layers. Modern systems have a large number of those abstraction layers. If we think of our application that we're interested in as being a networked application in which I have my phone and it's connecting to some server that's located somewhere, we then can think of it as two applications that are networked together. And there's a lot of abstraction layers underneath those to get that to work in reality. There are the abstraction layers on the networking side, which is not something that we focus on at all in this course. There's follow-on courses you can take. There's very well-defined abstraction layers in networking because there's a lot of standards associated with that. But from application layer all the way down to physical layer, when you say I am connecting to this website, well, what you're actually doing is connecting over an application layer protocol called HTTP, using TCP over IP, ultimately over 802.11g Wi-Fi that has the underlying physical layer associated with it. That's on the networking side. On the computing side, there's a somewhat fuzzier but relatively well understood set of computing layers from the software all the way down to the underlying physics that you have there. I won't belabor the point too much today, but from the application, I want to, again, communicate from my device to that server. There tends to be some sort of algorithm underneath it. I need to sort all my emails that are showing up in my email client. What algorithm do I use to do that sorting of those things efficiently? If you haven't taken those classes, you'll get an opportunity to do so. That algorithm, the logic of my code, is implemented in some programming language, and there's some underlying interpreter or compiler associated with that. Again, that's your choice of, do I use Java? Do I use C++? Do I use Rust? Do I use any of those choices available to me? There tends to then be that middle layer of software between your user program and the underlying hardware. That's the operating system, managing things like your devices and your processors in your system. Where we are primarily interested is in those middle layers in that stack here. Originally, someone who referred to themselves as a computer architecture would have expertise all throughout those middle layers there, from programming languages effectively on down. In more modern systems, we tend to have a little bit more specialization, and computer architects work in those middle three layers that we have here. We'll talk a little bit more about what those three terms mean on Wednesday, but I left off at operating system. Underneath that is the design of the instruction set architecture. For my processor, what are the instructions that are going to be implemented by it, and what are they supposed to do? I have an add instruction. It adds two numbers. What two numbers? How does it add those two numbers? Where does it put the result of adding those two numbers? That's something that's defined in the instruction set architecture. Underneath that layer is the microarchitecture. That gets to the implementation of a given ISA, of a given instruction set architecture. How do I actually do that addition? What type of data path elements do I have to be able to do that addition? And then underneath that is, you could refer to that as the digital logic layer, or in here it's referred to as the logic gates or the register transfer level implementation. Think back to your CprE 281 days. Hopefully not too far back and hopefully not too long forgotten, but the digital logic layer of, I have an add instruction. The ISA says it adds these two numbers and stores the results in this register here. Microarchitecture tells me, where am I going to lay that out, and how am I actually going to do that, and how many cycles it's going to take to do that. And then the layer below that is, how am I going to implement that adder? And there's many different ways of implementing an adder, and we'll talk about a couple of them later on this semester, but this is not primarily a digital logic course. And those are the domain of the modern computer architect. So what instructions should my processor have? How should they generally be implemented? And what type of digital logic optimizations are associated with that? There is an argument to be made, and I won't belabor the point too much because we're referring to a lot here in the very first couple of slides, is that this was thought of as the domain of the original computer architect, but modern architecture tends to be crossing a lot of layers again. So the choice, if not of the programming language being primary, but the choice of the libraries that we want to make as efficient as possible is something that computer architects do have to worry about. People who go to industry and work at Intel or work at NVIDIA or these other companies where they would have a hat that says computer architect, they tend to be somewhat specialized and say, I'm going to work on this particular machine learning library, and I'm going to look at the architectural decisions to make that library faster, excuse me. And likewise, while I say here on the slide that the domain of recent computer architecture doesn't look at things like circuits, now you're thinking EE 330 type topics, what we would refer to as VLSI in this department or below. That's not so much the case given the very difficult design decisions that are having to happen at the circuit and below level. That at least influences the computer architect, whether he or she actually has to make those design decisions. Certainly modern computer architects have to be aware of these layers. Still in this class, our primary focus is going to be on those three middle layers that we have here. So consequently, with regards to this class, there's various levels of representation that we have to be somewhat fluent in. And some of these you may already feel comfortable with, depending on your previous coursework and other experience. Others, I can assure you, will become fairly fluent in by the end of this semester. Referring back to those layers of abstraction, certainly in this class, we do have to have some familiarity with high-level programming, high-level language programming. We don't do very much that's very language specific. So I say, for example, C, and that's some C-like syntax there. If your worry is, well, I don't know C all that well, you'll still be perfectly fine in this course. There are some aspects that become programming language specific, and we'll talk about those when we get to those. There's no C programming assignments in this class, but you have to be aware of what's happening at the high level language, because a good part of what we do this semester is to look at that translation between the high level language and the resulting assembly associated with a given architecture. We become the compiler in this class. This is not a class on compiler construction. That is a fairly wholly separate field with a lot of computer science theory and quite a bit of engineering practice associated with it. But in this class, we become the compiler, and we look at that C segment that we have up there, and we look at, well, it's a lot of memory accesses. That's going to correspond to loads and store instructions in our target ISA, and we're going to become pretty fluent in assembly language this semester. And then below that, we also, at least at times, will be an assembler as well. That's taking your assembly language, translating it to the machine language, literally the binary code, the ones and zeros associated with that architectural implementation. And believe it or not, by the end of the semester, there's no tests or anything like this on this, but by the end of the semester, you'll be able to look at those 32-bit sequences and say, yep, those are load instructions and store instructions, because you'll be building it and you'll have such a deep understanding of what's happening. You'll at least remember the hex representations of a lot of these assembly instructions to be successful in this course. And that red bar there could be thought of as the hardware-software interface. The textbook for this class talks about that quite a bit, and that's where you're no longer designing software and now you're designing hardware. And computer architecture is a lot of that design of that interface. From our perspective, in terms of the levels of representation, we have the machine code. We now have to build some hardware to understand that machine code. And that involves hardware description using a hardware description language. In this class, we'll be using VHDL throughout. And then we touch upon, although this is not a class on digital hardware design, what's happening underneath that language at the hardware description level, how it gets translated to individual gates. And we do generally stop at individual gates this class. That's using a logic description or a logic synthesis tool such as Altera Cordis. I know you've used that in 281. We'll be kind of sort of using that again this semester, but not in a similar method as you would have used it in 281. For us, it's more of a black box. We hit and go, and assuming we did things correctly, things just kind of go at that point. I personally think, and I'm a little biased, I do research in computer architecture as my other day job. I think this is a very exciting time to be studying computer architecture. That was not always the case. There had been this well-established long history of, and this is a logarithmic plot here, of exponential improvement in computing on a year-to-year basis. We could talk about Moore's law and things like that at some point, but this exponential improvement in computer architecture performance, which was almost entirely driven by improvements at the circuit level and below. There were architectural improvements happening at the same time, but they were pretty subtle. And so there was computer architecture work happening, but it was the VLSI engineers who were really doing the very innovative things and the semiconductor engineers who were doing the very innovative things. That's what this chart is attempting to represent. My take on that is that we were able to see this exponential performance in part because we were able to just to crank up clock frequency in a fairly exponential growing path here. We can't really do that anymore. We're very limited in terms of how certain types of performance can be improved via just VLSI and semiconductor device improvements. The world is now back to being the computer architects, certainly for software as well, but it's back to being the computer architects world because we have to be a lot more innovative in terms of what our underlying architecture needs to look like to get any sort of either efficiency gains or just improvements in performance, those type of gains as well. And that's what I just was saying here on the slide. 10 years ago, that may have not been the case. 20 years ago, I would say it was definitely not the case. But now there's very much a paradigm shift happening, not just in academia, but certainly in industry as well, in that we are limited in what we can do in terms of new semiconductor devices. We are very limited in terms of how many transistors we can continue to pack onto a single chip. That term dark silicon is thrown out there. That's a way of phrasing that we can actually continue to pack more transistors on a given chip. We just can't keep them all powered up at the same time. So part of the silicon remains dark at all times for thermal reasons. There's a lot of different potential system designs that are now possible. They were always possible, but now they're interesting to study again. And we see a lot of work that's looking at old ideas that have become new again because the landscape has shifted such. There are many different problems that have been caused by that shift. I won't go into these right now, but certainly power and energy constraints is a primary one. We can put 20 billion transistors on a chip. Can we keep it powered on? Can we keep the energy within a reasonable envelope? Can we fit it all ultimately on a cell phone at the end of the day? There's no easy answers to any of those difficult challenges that face the computer architecture community. But it becomes a fun problem to explore for that reason. Going back to this course's focus, the title is Computer Organization and Assembly Level Programming, but our focus is on computer organization and design. So it's the design and analysis of those abstraction layers that enable general purpose computation, that enable the data path and the control elements for general purpose computation. There's a lot of different ways you can learn computer organization. And in fact, unlike some of other courses in our curriculum, computer architecture classes tend to be quite different depending on the institutional context. So CprE 381 is different than the equivalent course at other institutions, and they're all somewhat different from each other. Our philosophy in our department, it also matches the textbook's philosophy well, is to focus on a specific instance of computer architecture, a specific ISA, and ultimately a specific select few microarchitectural implementations, and learn how it works while simultaneously trying to also understand both general principles and some historical perspectives of how computer architecture has evolved. Other courses take the philosophy of, let's do architecture as a blank slate, let's create our own processor. There's nothing wrong with that approach. And I'm quite certain that after taking this course, if you are interested in creating your own processor, you can certainly do so. We're focusing on a specific instance that's extremely well documented and supported. Common question we get, this is meant to be said with something of a whiny voice, but I appreciate it as a valid perspective. And my question is, but I never want to build hardware. Certainly quite a few software engineers take this course. I'm very happy to have you. And you realize that you have your career path, at least in the beginning, fairly well set up, and you know what you want to do in life, and it doesn't involve building hardware. And a somewhat corollary question to that is, also, why should I have to learn about assembly code? Why? Who cares, right? The world today is JavaScript libraries that we glue together to get things working. And that's true to some extent, or Python packages that we click a button and just kind of works. That is true. The common answer that I definitely I buy into is, if everything goes well with your Python code, you don't need to know anything about the underlying hardware. Arguably, you don't need to know what's happening above that in the abstraction layers as well. It's not really a problem. But what does happen, if the program you're writing is slow? We can look at algorithmic tweaks. What's happening underneath that? What happens when things aren't working correctly? Are there issues with memory consistency, with multi-thread logic models and things like that? What if it actually consumes too much energy? I think if we stayed entirely in those higher level abstractions in terms of your training, you would have no way to really even intuitively think about what could potentially be happening below that, and to be able to debug it, to be able to at least reason about what optimizations could be possible to improve that. So another way to think about that is you get that exposure to that in this class. For some of you, this will be your only exposure to hardware and assembly level programming. For others, you're going to discover that you love it and you realize that you want to be a computer architect when you graduate, and that would be great. But that exposure should pay dividends for the remainder of your career, even if you never design a piece of hardware ever again. And you may not believe me that today. You may be saying, well, this is either a technical elective for me or just a necessary evil that I have to take. And I'm doing a lot of it. There's a lot of content in this course. Trust me for now. Talk to me at the end of the semester and then talk to me in 10 years. And we'll see if you found some value in this course. I have a little bit of that experience with students who've come back and talked about that. What you should already know, and now we're kind of briefly segueing into more syllabus issues. You should have some familiarity with high-level programming. You should have that CprE 281 knowledge base. We don't do a ton of refreshing on that in this class. So if you don't know what 2's complement is, I will remind you because it comes up pretty quickly in this class. Understanding powers of 2 and things like that, binary form in general. You should have a decent background in logic design from 281. I understand that's a couple semesters ago. Something of a running joke in this class is that you learn all this digital logic in 281, and really the only thing you use in 381, in which we're designing something quite a bit more complicated than anything you did in 281. The only thing you use are flip-flops and muxes. And that's true to some extent. The answer to many computer architecture questions, how do I do this? The answer tends to be add a mux. You should at least know and be fairly familiar with what a multiplexer is and generally what it's attempting to do. Don't freak out if today you're scrambling back looking for old notes. What is a mux? We'll remember that. We'll cover that again as a class. That's going to be fine. But that's generally what I expect from you between CprE 281 and CprE 288, which are the prerequisite path to get to this class. I do assume that you know those things coming into this. Like you to meet the staff. That is me. Just you can call me Joe, Professor Zambrino, Sensei. That's fine. It doesn't matter. Those are our teaching assistants. They are very much all sort of near peer TAs in that they've all taken this course, survived this course relatively recently. Together, I think we have pretty good coverage of office hours, of the lab sessions and things that we have here. I list the email addresses here, but I do want to add a caveat that email is okay. Email's fine for sort of, personal issues that you don't want to have available anywhere else for documentation and things like that. There are a lot of students in this class. My email reply latency, and I guess I'll add, I get a lot of emails as well, is going to be a lot higher than if you access through Discord or our other mechanisms that we have here. But those are our email addresses. I have my office hours set up. The TA's office hours are also now set up, but it depends on which TA, which day it's on. I also have my special teaching assistants who do help me along the way. Mostly exam gradings. They're getting older now. That's Joey's 12, Tessa's 9, and Johnny just turned 7 this week. Johnny helps me mostly on the exam grading. So when we get to exams and you're writing down your exam answers, that is my goal for you. Write the exam answer so that a 7-year-old can understand it and appreciate it, and then that makes the job of grading much easier because I can offload a lot of the work to him. That was meant to be a joke. Okay, this is the main textbook for the course. There are many different variants of that book. They are all extremely similar, but not identical. So just FYI, if you look at the book on your desk in front of you and you bought the ARM edition or the RISC-V edition, that's not ideal, but it's okay. I mean, we'll make do. I can probably find the electronic version of this book available for some folks. If you've already purchased another version of it, but that is the version that we use. This is still the MIPS version of the book, and it's the 5th edition. It's a pretty good book. I suggest taking a look at David Patterson and John Hennessy and take a look at their career path and what they've done. Not all domains within computer engineering have such a well-regarded, somewhat universal textbook associated with it. Another guide that I actually like quite a bit, it's freely available and I posted it on Canvas, is the Free Range VHDL guide. We will talk about that later, or really throughout the semester. The labs are very much a VHDL experience. This semester, VHDL is a little bit of a tricky language to Google help with, to look up errors, to try to say, how do I do this in VHDL? The language has evolved over time. There's just a lot of wrong content out there when you Google certain things. That guide is very readable, and as part of your lab experience, you will be reading through it effectively chapter by chapter. I'm a big fan of it. There's many bad guides out there. There's many stale pieces of stale information about VHDL out there. Taken together, I'm pretty content with the textbooks and the resources we have, excuse me, for this class. And I think you will eventually appreciate them. Definitely here to help, but that communication is key. Canvas is a pretty static thing. It's mostly done for the semester, but there you will definitely see the layout of how our semester is going on a week-by-week basis. If the question is, where is this PDF or this link, the answer is on Canvas. It's all on Canvas. There's no class web page for this class outside of what I've put on Canvas. It's also where we'll be submitting things. So it's our online submission. It's where you'll check the grades for things that you have submitted. We are also, as many of you, but not really all of you know, attempting to use Discord for all of our class discussions, and as well as our virtual office hours. We'll see how it goes. It's an experiment. It's my first time using it. I'm not necessarily an expert in using it. I'm always open to suggestions for how to make the experience better for you as students. If you haven't gone there yet, please do go there. That's probably the best way to reach myself for the TA team this semester. And in my experience in previous semesters using other tools, we can get a pretty quick turnaround time. Something I did talk about in the video I've already posted on Canvas for the first week of lab is, the labs in this class are hard. Not trying to scare anyone. The complexity will ramp up as we go throughout the semester. We're building a processor. There's no easy way to do that. But none of the individual bugs or error messages or individual issues that you should face in these labs are ever meant to be real showstoppers. You should not have a 2-hour bug in this class, meaning a bug that takes you 2 hours to resolve and work around. either a compile syntactical error or some simulation error, even a conceptual error. This class is filled with dozens of 2-minute bugs. And the experience you have in this class, certainly in the lab environment, is going to be dictated, I think, in part, of course, by your own ingenuity and work ethic and ability to reason through these issues, but also in your willingness to reach out for help. It's a quick Discord message. I've gotten this compiler error. Of course, review what's already been posted. I've gotten this compiler error. What do we think is going on? You'll get a pretty good answer, and you can turn those 2-hour bugs into 2-minute bugs. And that's how you deal with the complexity, or can deal with the complexity in this class. Because otherwise, it can sneak up on you. Certainly, Lab 1 is going to be pretty easy. It's just making sure everyone can access the tools that we have in this semester in this class. As we start to build this processor, the complexity does ramp up here. I wanted to open up Canvas very briefly here. And in Canvas, this is the main page. I said there is no class webpage. I kind of just turned Canvas into a class webpage for the class. There you have some of the same information listed, including the actual office hours. It's got the link to this Zoom. So those of you here already have that link. It's got a link to that Discord if you haven't yet added here. Where you'll find a lot of your time would be on that schedule page. And that is what is going to continually be updated as I continue to add content this semester. That is my attempt to kind of project what I think this class is going to be on a week-to-week basis. We're in week 1, we're in the introduction. If I click on that, you'll see I have the slides uploaded. So there you go, they're already there. And they should generally be there before the lecture starts, and generally well in advance of the lecture starting. They're pretty stable from semester to semester. This is where I'll be uploading via YouTube. Please be sure to like and subscribe. The actual videos of our time together in class. That may take a couple hours after class, but I will do so, as well as other video that I will create as I have time to review the syllabus. I'll be making a video on that probably tomorrow, just to make sure I've covered all the syllabus issues with everyone. And that'll be our week-to-week content that you'll be accessing. I'll note that we have listed generally on Wednesdays. If Monday is kind of core content Monday, Wednesday can be thought of as sort of quiz or assessment Wednesdays. And we do have a quiz this Wednesday. The first one is going to be truly just a check that we can get Canvas working for quizzes. On Wednesday, we will be all logging into Canvas. We'll all be clicking this link, and we'll all just be taking a quiz. And that's going to be happening during our scheduled lecture time. So a lot of people have asked, well, do I need to come to class? That is a difficult question for me to answer. And it's actually more difficult this semester than in most semesters. In most semesters, my answer is kind of tongue-in-cheek. Well, what do you want to learn this semester? Do you think there's any value in coming? Then come. That's my somewhat tongue-in-cheek answer. This semester, with our online format, in which there's a pretty clear directive that we're supposed to have meaningful, synchronous time together as a class, this is my mechanism for trying to do that. So I'm never going to pull a pop quiz on anybody. I don't have time to do that anyway. But you can look at what's scheduled here, and Wednesdays are generally set aside. It's not the entirety of Wednesdays. It'll be 5 minutes during those Wednesdays for these quizzes for a little bit of touching base. Generally, the quiz will have one question for you and one question for me, and we'll see what that looks like when we get started. And then we have our Friday time together. I may go off tangents on Friday. We can think of that as Fun Friday, but something that's not necessarily strictly textbook stuff on Friday. So, the question is, do I need to come to class? Do I need to review materials in class? My hope is there's some value added in my creating all this content for this class. There's a lot of complexity in this class ultimately. Some of it you can learn, certainly autodidacts can just learn just by reviewing the textbook. Some is currently only up here and eventually will be in video form. And I want to make sure that you have that opportunity to learn that material as well, because there are some things the textbook doesn't cover. So long story short, with regards to syllabus and our general weekly schedule, um, there's a lot of stuff in this class. Each week in general for this class, you can think of there being our 3 times that we get together in person over the internet, one of which has a brief assessment, a brief low stakes assessment. Each week, there's your scheduled lab time. I'll post a reminder about that. All of our lab sections are on Wednesdays and Thursdays this semester. Please attend your lab this week. We do have first week lab. I know some courses don't, but we do, where you'll be doing your orientation lab. And then there is a homework that'll be assigned generally on Fridays of each week. When you click on this, the link won't be active yet, but it will be on Friday. And you'll generally have a 7-day period to work on and submit those homeworks. So that they have a different flavor to them. So the quizzes are low stakes assessments. I am perfectly fine, and the outcome of previous semesters was effectively everyone gets 100% on the quizzes. So you physically and mentally are present, and you're fine on those. The labs are where you will be spending ultimately a decent amount of the time in this course. It's more than 50%, I would say, in terms of your brain and physical energy in this course spent on the labs in this course. And then there's weekly homeworks that are very much textbook type problems. You could probably Google and find solutions if you wanted to. Ultimately, when it comes time for exams, which will be drawn from that same class of content, you'll maybe struggle a bit more if you do that. Those are also relatively low stakes assessments as well. I'm going to leave things here for today because there's a lot more syllabus stuff that I would like to cover. Key takeaways for today are remembering what are the major components of a computer, the 5 parts of a computer. Where we're going to be focusing on are really those middle 3 layers: instruction set architecture, microarchitecture, and the digital logic or RTL implementation of the same. And then go to lab this first week. That's our other major takeaway for today. I will stick around, not in Zoom, but in Discord for office hours if you have any one-on-one or group questions that you have for me. Otherwise, this will get uploaded at some point later today. And thanks. I think it worked out somewhat okay. We'll see how things go for future classes. We're going to try to let the technology work for us and not fight it all that much. But I'm looking forward to this semester, and I'm looking forward to helping everyone learn a lot more about computer architecture and a little bit about assembly level programming as well. Okay, thank you.